Welcome, future builders and curious minds. Today we're diving into the microscopic world of clay minerals. You might think of clay as just mud, but in civil engineering, these tiny particles are incredibly powerful. They form the backbone of many soils and have a significant impact on our structures. Think of them as the microscopic Lego bricks that make up the earth beneath our feet, affecting everything from foundations to dams. So, what are these tiny titans made of? Clay minerals are primarily composed of silica tetrahedra and alumina octahedra, arranged in layered structures. Imagine stacking sheets of aluminum foil and sandwiching them between layers of rice paper. This layered structure is key to their behavior. These sheets are incredibly thin, often only a few nanometers thick, giving them a massive surface area. This is like having a huge number of tiny sponges, ready to interact with their environment. The clay mineral family is diverse, with common members like kaolinite, light, and montmorillonite. Kaolinite is a relatively stable clay, often found in high-quality ceramics. Elite is more like a flaky mica. But montmorillonite, that's the real showstopper for civil engineers. It's known for its ability to absorb and hold vast amounts of water between its layers, making it incredibly expansive. Think of it like a super absorbent sponge that can swell to many times its original size. This is where things get interesting and problematic. When clay minerals, especially montmorillonite, come into contact with water, they can absorb it into the spaces between their layers. This causes the clay particles to push apart, leading to swelling. Think of a dry sponge suddenly placed in water. It expands significantly. Conversely, when the water dries out, the clay loses water and the layers collapse back, causing shrinkage. This cycle of swelling and shrinking is a major concern in civil engineering. So, how does this swelling and shrinking affect our environment? Foundations are particularly vulnerable. When expansive clays swell, they can exert significant upward pressure, lifting and cracking foundations, walls, and even entire buildings. Imagine trying to build on a giant, unpredictable mattress that constantly changes its firmness and height. Conversely, during shrinkage, voids can open up beneath a foundation, leading to settlement and instability. It's like building on a foundation that's slowly sinking and cracking. It's not just foundations. Roads built on expansive clay can develop wave-like deformations as the subgrade swells and shrinks with changing moisture. Think of a road surface rippling like water. Dams and embankments built with these clays can experience differential settlement, compromising their integrity. Imagine a long, rigid structure, like a dam, slowly bending and cracking, because the ground beneath it is unevenly moving. Fortunately, we have ways to manage these tricky clays. Strategies include over-excavation and replacement with non-expansive fill, chemical stabilization, like lime or cement, or using specialized foundation designs like deep piles. Think of it as preparing the ground carefully, like a chef preparing ingredients before cooking, to ensure a delicious meal. Each method aims to control or eliminate the water interaction that causes the problematic volume changes. The most crucial step in dealing with clay minerals is proper site investigation. Before any construction begins, engineers must identify the presence and type of clay minerals, especially the highly expansive ones like montmorillonite. This involves soil sampling, laboratory testing, and geological surveys. It's like a doctor diagnosing an illness before prescribing treatment. Identifying the specific illnesses, the clay, allows us to choose the most effective medicine, the mitigation strategy. So, from their microscopic layered structure to their dramatic impact on our infrastructure, clay minerals are truly tiny titans. Understanding their composition, behavior, and interaction with water is fundamental for any civil engineer. By respecting these natural forces and employing sound engineering principles, we can build safe, stable, and lasting structures, even on challenging ground. Thank you for joining us.